Okay, yesterday we have discussed about unaligned transactions, aligned transaction, right strobe signal, secured access, privileged access, all these things we have discussed. So in that way, how we are calculating the aligned address and then unaligned addresses. Okay. Next, today we will discuss about byte lane selection equations. How which byte lanes are valid byte lanes and then which are invalid. Okay. So these byte lanes, how we will calculate? We can see here. See, how we will calculate means we have a uh, unaligned start address. Whatever the unaligned start address, that first byte will be the unaligned. The next, from the next onwards, it should be aligned. Okay, so the number of bytes, how we are transferring the number of bytes, data bytes, that is the total number of bytes per bus, how we are transferring. Then data width, whatever the data width we have given, should be divisible by 8. Okay, so and then aligned address calculation, aligned address equal to int of start address by data bytes into data bytes. In this way we will calculate the aligned address. That means start address they will give you like 0x100 or 0x 04. Okay, so in 104, in this way they will give the start address. And then int of start address by data bytes. Data bytes means total number of bytes, that um, burst size into burst length. Based on that we will get the data bytes here. And then size, that should be number of bytes transfer in the first bit. That means your data byte size means 2 power AxSIZE. Okay, so AxSIZE is the number of data bytes we are calculating. This defines that data bytes. That means per packet or per bit, how many bytes of data you are transferring. Suppose your size 2 bytes of data you are transferring for 1 bit. Integer of x means that is the round off value. That means nearest integer value we are calculating. And then byte lanes, each byte lanes, how many bytes of data we are transferring. Suppose byte lane 3 down to 0 means 4 bytes of data you are transferring. Suppose your byte lane is 2 down to 0 means 3 bytes of data you are transferring. And 1 down to 0 means 1 down to 0 you are taking means 2 bytes of data you are transferring. Then byte lane selection equation, lower byte lane and upper byte lane I am calculating here. Lower byte lane, how we will calculate here is you need to have a start address. This they will provide you, and then minus integer of start address by data bytes into data bytes. Then you will get that aligned address here. Okay, so aligned address you will get. After that you calculate the aligned address and start address, you will subtract means lower byte value you will get. And also upper byte lanes means this lower byte lane gives you the indexes of your first valid data. So which index? 0th index, first index, second index, third index. So that index will give you. Suppose I'm transferring 4 bytes of data per bit. That means 0th index, first index, second index, third index. That means my start address is 0x100. This is the start address. Index will be starting from 100, and then first index 101, second index 02, and then third index 103. So if you add plus 1, then we will get the next address 104. So in this we calculate the address here, and then lower byte lanes address we will calculate, and then whatever the aligned address we got, so that aligned address plus size minus 1, and then same way we will calculate the aligned address data. So based on that we will get the upper byte lane. Upper byte lane, see how we will calculate the aligned integer of start address by byte lane, data bytes into data bytes. Okay, so this, in this way we will calculate the aligned address. Base address we will get the upper byte length. So that means uh, byte lane. Suppose 3 down to 0, this is the lower byte lane, and then 3 is the upper byte lane. So you will calculate. Suppose if you are considering one example like start address is 101 and total size is 5 bytes and then data bytes is 4. Okay, so in this way I will calculate my next address. So that means aligned address I need to. How we will calculate the aligned? Just take that aligned address, start address they will give you. Okay, start address is 1001 they have given, and then size they have mentioned like what is the size, your data size, data bytes is 4. Okay, data bytes is 4. In that lower byte lanes are 1 and upper byte lanes are 3. How they are calculated, we need to consider the formula here. Okay, so here I am calculating size is, data size is 4, and then lower byte lengths, how we will calculate lower byte lengths, that is the value, see, start address minus integer of start address by byte lengths into data bytes. So integer of that is the integer of start address. So start address is, what is the value, 100, so 0x1001, so divided by 4 and into 4. Okay, so this should be divisible by 4, then you will get the started so value is nearly approximately equal to 1000. So this is the 1000. Then lower byte lengths, your started 0x1001 minus you have aligned address 0x1000. Okay, then one value we will get. So 1001 minus 1 we are getting. In that way lower value we got, and then same way upper value we need to calculate, that size minus 1. Size minus 1 means 4, right? So upper byte lengths we will calculate here. Okay, upper byte lengths, how we will calculate, uh, aligned address. What is the aligned address? 1000, right? So 0x1000, this is aligned address, plus size minus 1, your size is 4. Okay, size minus 1, 4 minus 1, 4 minus 1, and then minus of integer of whatever the address we have calculated, that should be same 1000. Okay, 0x1000. Okay, this 1000 and this 1000 will be 4 minus 1 is 3, so then upper byte lengths are 3. So that is the reason we got upper byte lengths are 3 and lower byte lengths are 1. So then right strobe signal should be starts with 101. Okay, so then the unaligned address. Okay, so aligned address, this byte lane I don't have any data, so that's why it is 0, because it starts from 1001. Okay, so 1001 is the byte lane index, that is the first index. So in this bytes of data address, in this address I am having my value of data. So in this way we will calculate the byte lane selection. So and also here start address is the 1000, and then 1001, 2, 3, 1. So in this way they are giving the different start addresses. So all this 1000 also started aligned address is 1000, 1001 also aligned address is 1000, and 1002 also aligned address is 1000, 3 also aligned address is 1000. Then lower byte lengths for 1000 is 0, and then upper byte lengths are 2. That's why 0 to 3 we are getting. Then all bytes are valid because it is a aligned address. And then 1001 we are starting with 1 here. So then what is the byte lengths valid here? So 1001, so 1 upper lower byte lengths are 1, upper byte lengths you need to cross with 1 to 3. So then here I am having the byte lane is only one value valid, that means 0 1 is the valid one. So that means remaining values I am considering as a 0. And then 1002 here, 2 byte lanes are valid here. So lower byte lanes are 2 and upper byte lanes are 3. So then 2 to 3. So 2 to 3, then 2 byte lanes are valid. So 2 and 3 values should be valid. And then so 1003 means upper byte lane is 3, lower byte lane is also 3. So based on that, 3 down to 3, 3. So byte 3 is valid. So 1 2 is that invalid conditions. And then so this is the way we will calculate the byte lane addresses. Are you understood? So fixed burst calculations, how we will calculate the burst types. 4 types of bursts we have in that: fixed burst, okay, fixed, increment and wrapping, and then reserved not using. So in that way we will calculate in this fixed burst. How we will calculate that? So slave read, write data. So that means slave is reading the data. So our master is reading the data from the slave. In that, all the addresses are same. We are whatever the addresses we are sending, all the addresses are should be same here. Just give me a minute. How we will calculate the fixed burst calculation? The fixed burst means the address should be same. Whatever we are writing the data to the slave, that same address we are following, that same address we are reading the data. That is the fixed address. So address remain should be constant. Every transfer we are maintaining the same address. That is the fixed address calculation. Okay, so here address remains constant for all beats in your burst of transaction. Okay, see how to fix the burst is working here. See, master is sending single address. Whatever the address we are having, that is the start address. So the master is sending the different beats of data: beat 0, beat 1, beat 2, and so on. So beat n. Okay, all the addresses should be, all the beats are having the same address: start address, start address, start address. All the addresses should be same. So there is no address increment here. Same address you are writing the data, from the same address you are reading the data. Okay, so here the fixed burst is size, burst size is 2 bit. Then 2 tick B00 is the fixed burst, and that means 01 means increment, and 10 means wrapping, and 11 means reserved. Okay, so the start address, whatever the all bits you are transferring in your data transaction, so all the bits are having the same address, that is the start address. How we will calculate the uh, byte lanes, and then how many beats are you are transferring means, see how many beats are transferring, the number of beats you are transferring for one lane. Okay, one so it will tells that Ax length. So actual beats should be the formula: actual beats or burst beats, okay, or burst length. So burst length will tells you that how many beats you are transferring, that is the actual beats. That means Ax length plus 1. Similarly, Ax size we will calculate that, that is the burst size. So 2 power Ax size. So this burst size will tells you how many data bytes are transferring per beat. Okay, so here there is no address calculation is required, because all the beats are having the same address. But that address we need to calculate, is that aligned address or unaligned address, we need to calculate it. And also not cross the 4 KB boundary. 4 KB boundary we are not crossing that. So based on that we will give you the fixed address here. Okay, so how we will calculate the start address here? So the start address, whatever the burst we are starting, so that gives you the whatever the beat you are transferring, that is the start address. Each and every beat having the same address, that is only start address. And then AxSIZE, we know that how to calculate that, data bytes equal to 2 power AxSIZE. And Ax length, we know that, so how to calculate the burst length, that is Ax length plus 1, and the type is 0 0. So the address, n addresses, whatever the n address we have taken, all that addresses are taking as start address. So that is the fixed burst calculation. In this fixed burst, whatever the address they have provided, that address should be same here. Okay, start address is that 4000. This 4 all 000, that means your Ax size is 2. That means how many beats are how many bytes of data you are transferring? Data bytes is 4. And then Ax length is 3, and then actual length is what? 4. So that means beat 0, 4 bytes of data you are transferring, and beat 1 you are transferring 4 bytes of data, and beat 1 we are transferring 4 bytes, in beat 2 you are transferring 4 bytes data. Okay, and beat 3 you are transferring 4 bytes. Okay, all the 4 bytes are having same address. You are transfer, this is the example of 4 bytes, 4 bits. And then this example is that size is 1, that means data bytes is 2. That means in every bits 2 bytes of data you are transferring, but Ax length is 7. So total 8 bits of data you are transferring. For all 8 bits you need to maintain the same address. Okay, then total transfer should be 16 bytes, because 8 bits into 2 bytes. Okay, 8 bits into 2 bytes, you are transferring 16 bits. Similarly, you can calculate the remaining things. So that is the, see, start address is that 05000104. Same address we are maintaining that. And then Ax size is 1, that means 2 bytes data you are transferring per bit. And then data bytes is 2. After that Ax length is 7. Then actual length is 8. So then all 8 bytes of data you are maintaining the same address. Okay, same address you are maintaining that. See, so 1004, that is D0, D1, D2, and then D3 you are sending that 2004. Then 1004, 1004 only we need to maintain the data. So all the data are same. Okay, all the 8 bytes of data you need to maintain 500104 only. Okay. So here I am calculating the fixed burst calculation. That means, so you need to start with start address is 1000. This is your boundary, and then before that address you are incrementing. So this is, in this way you are incrementing the addresses. That means 0. So what is your final address for 100? This is your uh, 100, this is your boundary. Okay, so this is your boundary. How I am saying that 4 kb boundary, 4 kb boundary means 4096, right? So this is the value related to 4 kb boundary. How I am saying that? So this is that 0 into 16 power 0, and then 0 into 16 power 1, and then 0 into 16 power 2, and then 1 into 16 power 3. Okay, 16 power 3, that means 256 into 16, that value is 4096. Okay, so this address does not cross that. If you start any other address, so then it will cross the address size. Okay, so that means you are starting with some 1001, means fixed burst is not obeying here, because you are crossing that 4 kb boundary. This 4 kb boundary is not allowed. Crossing the 4 kb boundary is not allowed in the fixed burst. See, 1 into 16 power 3 plus 1 into 16 power 0, that means 4097 you will get the value. So this value will be crossing the 4 kb boundary. That should not be allowed in the fixed burst. Okay, that is the invalid addresses. So now we will go for increment burst calculation. How we will calculate the increment burst here? See, we need to consider some examples related to increment burst. So for that, I'm taking the increment address. So for each data transfer, so how many data bytes you are transferring for one beat. So each and everything the address should be increased. See, beat 0 you're making as the address 0 and beat 1 address 1 incrementing. In this way the address should be increased. How we will calculate the next address means, so address n equal to whatever the start address you have. Okay, start address plus n into number of bytes. So n is here means is a first address or second address, third address or fourth address, depends upon the value we will place this small n value. Okay, that n means 0, 1, 2, 3 and so on. So we are giving the values. Same formulas here also we need to maintain. And then burst length, what is the burst length I'm having here? It is an AxI4 means they are having 256 beats of data we are transferring. Okay, so then a actual beat should be Ax length plus 1. Length plus 1 is the value we are considering. Okay, so and then what is the formula for subsequent addresses? What is the previous address we have? Previous address plus data bytes we need to add here. So in that way we will calculate the next address. And this is also do not cross the 4 KB boundary. That means 4096 value does not cross this. Okay, within the value only we need to maintain the addresses. Okay, if we cross that address means that is the not allowing invalid address. Okay, so for that we will calculate that addresses here. So how we will calculate the address depends upon the AX size, AX length, and then nth address. See, nth address, how we will calculate? Start address plus n into data bytes, and n equal to 0, 1, 2, 3 and so on. So up to AX length we are calculating. Suppose 8 bits, AX length is 7 is given. 7 plus 1 means 8. So up to 8 bits of data we are placing there. So for that we will calculate that next addresses. Okay. So how we will calculate the next addresses? We have same different type of addresses. This is the start address, and then burst size is 2. Okay, then data byte should be transmitted as 4, and then 4 data bytes we need to transfer, and then AX length is 3, then actual length is 4. So 4 bits you are transferring, and each byte each bit 4 bytes of data you are transferring. Then start address is 1000 here, and then how it is incremented 4, and how we will get the 8, and how we will get the C means we need to follow this formula. So what is the formula here? Start address plus aligned AX length plus AX length into data bytes. So in that way we will calculate the last address. So this is the last address, and then nth address we will calculate, that means n into number of bytes. See, this is the example we have. So start address is 1000, data bytes is 2, and then size is 2, and then length is 3. Then we will calculate the next address. How we will calculate the next address? Tell me. So what is your start address I am giving here? My start address is 1000, right? Start address is 0x1000. So this is my start address. And then what is my size here? Just I am mentioning AX size. 2. AxSIZE is 2, and then AX length is 3. Then here burst size we will calculate. Okay, burst size, that means data bytes we will calculate. Burst size is equals to 2 power AxSIZE. Okay, so 2 power 2. 2 power 2 means 4. Then 4 data bytes. Okay, 4 data bytes we are transferring. And then AX length is 3. Based on that actual length we will calculate, that is the burst length. Burst length equal to, what is the formula? AX length plus 1. So 3 plus 1 we will get 4. So then 4 beats you are transferring. And each beat, how many bytes are transferring here? 4 bytes. Okay, so here beat 0, this is beat 0, beat 1, beat 2. Okay, so beat 0, 1, 2 and 3. Okay, we need to calculate the address for this. Okay, beat 0 address, how we will calculate that? So address n, what is the formula we have? Address n equal to start address. Okay, start address, what is the start address we have? That address we need to calculate it, and then start address plus, what is the formula for next one? Start address plus n minus n into data bytes. What is that n? N is that up to here AX length is 4, right? So actual length is 4. Then n equal to, starting from 0, 1 and 2 and 3. Up to 3 we will consider that. Then n into 0, n into data bytes. N into data bytes is the formula. Then start address is, what is the value? 0x1000. So 1000 is the start address, and then n is that 0. That means I am calculating the address 0. Okay, address 0 I am calculating. That means 0x1000 plus 0 into data bytes. What is the data bytes value? 4. Okay, so 4. Then we will get the value is 0x1000. Okay, in beat 0 you are transferring 4 bytes, each are having 4 bytes. 4 bytes of data in this start address is 0x1000. So this is my start address. And then next address, beat 1, how we will calculate the beat 1? Same thing, whatever the start address we have, 0x, I am calculating the address 1, 0x1000 plus n value is 1, and then number of beats should be, data bytes should be 4. Then you will get that address is, next address is 0x1004. Then next address is 1004. Similarly, next address is 2 into 4, 1008. And then next address is 3 into 4, that means 12, 100C. In this way we will calculate the next addresses. So that's what we have shown the previous slide. This is the data 0, start address is 1000, and then data 1, 1004, 1008 and 1000C. Then this address we need to calculate the last address. How to calculate the last address? So start address plus so in this way we will calculate the next address, last address. Okay, last address, that means the boundary we need to we don't cross that boundary. Okay, last address, how we will calculate that? We will calculate the last address based on that previous address. What is the address we have? Okay, last address we will calculate based on that formula. So what is the formula we have? Start address plus actual beats into data bytes. Okay, so that is the start address. Start address plus data bytes. That means actual bytes. That means burst size. Burst size into burst length. Okay, so this is the formula. So start address is 0x 1000 is the start address plus what is the burst size? Burst size is 4. Burst size is 4, and then burst length is also 4. Okay, so then what is the value we got? So this is the hexadecimal value. We will consider 1000 value plus, so 4 into 4 means 16. Okay, what is the value we are getting? 16 means that is the final last value we are getting. That last value, how to calculate this means, so this is the 16 means that is the decimal value. Decimal value should be converted into hexadecimal. 16 should be divided with 16. One time we are getting, so 10. So then this should be converted into 0x 1000 plus, so 16 should be converted into hexadecimal, so 0x10. Okay, so then last address is we are taking this 0x1010. So this is the last address. This address does not cross this. Okay, do not cross this address. That is the last address. Okay, so this address should be less than or equal to 1000. Okay, so then this 4k boundary do not cross this, then 1000 do not cross this one. Then the last address should be crossed here. That means 1010 means it is crossing. So this address should not be crossed. If we cross this means that address should not be allowed in your incremental burst calculation. After that, wrapping burst. How we will calculate the wrapping? Okay, wrapping burst calculation. So that means we need to calculate the lower boundary and upper boundary. If we reach that upper boundary means again wrap around to start address. In this way we will calculate the wrapping boundary here. So based on that wrap address, what is the value we are getting? Just give me a minute. So wrapping boundary, in that wrapping address, we need to calculate the two boundaries. Upper boundary we need to calculate and lower boundary we need to calculate. Based on that upper boundary and lower boundary, so it will assigns that addresses. Okay, so the next address, based on that we will assign the next address. So then we will calculate the wrapping boundary here. If it is crossing that 4 kb boundary, again wrapping around to first address. Okay, that is the wrap boundary calculation. In this wrap boundary calculation, each and every one having their unique address. Based on that, AX length. Okay, AX length plus 1 into number of bytes, that is the wrap region size, we will calculate it. Okay, wrap address in this upper boundary, once you reach the upper boundary, again wrap around to the lower boundary. So that means you need to start from the again start address. And then, so how the burst value will taking, that burst type is 10 means wrapping burst we are taking that. So in that start address must be, we need to aligned address, we need to consider that. How we will consider that aligned address? See, this is the formula. Start address should be aligned, that is the starting address. And then size, how we will calculate the size here is um, AxSIZE. Okay, so AxSIZE is the burst, AxSIZE, based on that AxSIZE we will calculate the burst size, that is number of bytes per bit we will calculate it. And AX length, depends on the AX length we will calculate that burst length. And then wrapping region, which region we are wrapping that, that means AX length plus 1 into number of bytes, that means total transfers we will calculate here. Okay, so that aligned address, aligned start address, we need to consider that, that is the aligned start address, that is the wrapping boundary, lower boundary. So how we will calculate that? Start aligned address equal to aligned start equal to int of start address by wrapping region size into wrapping region. Okay, so that is the formula. And then upper boundary, how we will calculate that? So just we need to add that aligned address, that means aligned start plus wrapping region minus 1. So in that way we will calculate the wrapping boundary. So upper boundary we will calculate that. And then address for number of bits, how we will assign the address bits, same way. So started aligned address, that is the start address we are taking. And then start address plus n into data bytes minus aligned start. So based on that aligned start, so we will calculate the address n. So that means whatever the modified region we have, so based on that we will calculate the wrapping boundary here. Okay, so same thing, what is the formulas we need to remember here? So aligned start address, we need to calculate that. Aligned start address, what is the formula here? uh, Aligned start wrapping boundary calculation, that means step by step calculation of wrapping boundary. So we need to calculate this aligned start address. Okay, aligned start, how we will calculate the aligned start here? Int of integer of start address by wrapping region, right? Wrapping region we need to calculate that. Into wrapping region, that means total transfer only. Okay, wrapping region, how we will calculate that? Wrapping region equal to AX length, that means burst length into burst size. Okay, burst length into burst size, that means burst length, how we will calculate that? AX length plus 1, AX length plus 1 into 2 power AW size. Okay, not AW, AX size. Not only write, it's also read also, we will consider that. Okay, so that is the value. Here what we are giving the value, AX length is 3. Okay, suppose you consider that, previously we have considered AX length is 3, and then burst length is or actual length is, what is the value? 3 plus 1, that is 4 bytes, 4 bits you are transferring here. And also size, AX size is 2. Okay, so based on that we will get that burst size That means 2 power 2. 2 power 2 means 4. Burst size is 2 power 2, 4. Then wrapping region should be 4 into 4. That is 16 we will get. Okay. So that 16 we need to calculate the aligned start. Aligned start, how we will calculate that? Int of start address we need to mention, right? Okay, that start address what we have mentioned in the previous slide. Okay, your start address is 0x1004. Okay, 0x1004, that is the start address. And then wrapping boundary is 16. So this is also 16. So then again, so this 1004 is also divisible by 16. So then your integer address should be calculated nearly approximately equal to, so 0x1000. So this is the aligned address. Okay, so aligned address we will calculate here. So aligned address, what is the value we are having? That is the 1000 value we got. Then wrapping region, this is the aligned address. Then what is the formula for upper boundary calculation? Upper boundary, how we will calculate that? Upper boundary means aligned address we have, right? So this is the formula. So upper boundary calculation, what is the formula? Aligned start, aligned start is 1000, we will take that. Aligned start is 1000 plus start address plus n into data bytes minus aligned start, that is the formula. Okay, so what is the formula we have? Aligned start, aligned start, that is the, this is the aligned start. Aligned start is 1000 plus what is the value we have? Start address. Okay, start address is different, right? Start address is what is the given? This is the start address, 1004 is the start address. So we have start address, and then what else we need? Start address plus n. What is the n value we have indicates that? So next address we will tell you that next address, based on that n value we will have up to that AX length into what is the value? Data bytes. Data bytes means burst size. Data bytes is the burst size. This is the burst size. So 4. So this is the data bytes we have calculated. Data bytes are 4. And then data bytes, after the data bytes, what is the next value? Minus aligned start. Okay, minus aligned start. Okay, so we need to add the values here. Aligned start address, what is the value? So 0x1000. So 1000 is the value, and then start address is what is the value here? Here we got. So that is the region we got, right? So aligned at what is the upper boundary value? So 0 start address is 0x1004, and then number of bytes n into, if you calculate that 4 bytes you are taking, right? So then here data bytes is 16. Suppose you are taking the first byte, so then you need to consider this 16 here. Okay, upper boundary is the 1000 value, and then here we will get number of n into number of bytes. Data bytes is the value. What is the value we got here? Align start is 1000. So data bytes is that number of bytes is 4. 4 into 4, 16 minus align start is 0x 1000. Okay, so then we got the value like so this is the start address 1000 minus 4 is the 4, so this is the address value 0x 1000 plus uh, this 4 value we got. This is also start address, that means aligned boundary, right? So this is also will consider 1000, this 1000, this 1000 is cancelled, and then 16 minus 1, so that minus 1 we will calculate the upper boundary. So whatever the value we got, so this is all about the value, and minus 1 we will consider, that is the upper boundary. Okay, so that means 1000 plus 16, that is the 100, f is the value. So 15 means f, right? 100 f, this is the upper boundary. Are you understood how we will calculate the upper boundary? Okay, so fine. So based on that upper boundary, we need to add the start address plus n into number of bytes. Then other data bytes we will calculate that. So start address plus n into number of bytes. What is the value we got? Start address is that 0x 1004 is the start address. So then beat 0 you are calculating. For beat 0, what is the value? So this is the start address plus uh, this value. So what is this value? N into number of start address plus n into number of bytes. Okay, start address plus n into number of bytes, that is the 0th byte you are considering. Then number of bytes is 4. 0 into 4. Then you are getting, so 0x1004. That is the byte 0 address. Okay, so byte 0 address, so that is my address for the nth value. So and again beat 1, because in this way 4 beats up to we need to calculate, right? So then again start address is 0x004 plus first byte, so first beat, so that means beat 1. In this beat 1 we need to calculate it 1 into 4. Then we need to add this value where you are adding, so 104 plus 4, that means 1008. So this is the next address. And also beat 2. So beat 2, how we will calculate? Again 0 start address 1004 plus n into, this is the formula. Okay, start address plus n into data bytes. N into data bytes. Okay, so that is the formula. N is the second beat you are calculating, beat 2, and then number of bytes is 4. Then 0x8 plus 4, that is C. So 0x100 C, this is the value. And then next address beat 3. Okay, so beat 3 we are considering 0x 1004 plus 3 into 4. 3 into 4 means 12, so that means 16. So then next address is 0x1010. So 1010 means I told you that this is the 12. 12 plus 4, 16. 16, how we can write the in hexadecimal? 10 we will write. So 16 in hexadecimal we will write it as 10. Okay, so then 10 is added to 1000 means 1004, then we will get 1010. Okay, so this boundary is crossed, right? Okay, so what is the aligned, what is the value we got? 100 f. Okay, 100 f is the upper boundary. This upper boundary is crossed or not? So it is crossed. 100 f is the upper boundary. This is my upper boundary value because we calculated the upper boundary. How we were calculated? So this is the start aligned address we have calculated. So aligned address, aligned start, this aligned start and aligned start is calculated, and then aligned address plus number of bytes into total number of bits minus 1. So in this way we have calculated, that is the 100f. Okay, that is the upper boundary. Then upper boundary is reached. Then again wrapping around to this bit 3 is again wrapping around to start address. Okay, so again it is wrapping around to 1004. Okay, start address is 100. Okay, so that means in beat 0 it is starting with 01004. Okay, so and then again reaches to 1008, again 100 c we have, then 1010, this could be wrap around to start address, that means 1000. Okay, 1000, this is my start address. In this way we are wrapping around this. Clear how we will calculate the wrapping boundary? So that's what he is saying there. See, um, in this way we have calculated that. See, upper boundary we have 100, so 0x 1000, and then number of bytes is 16 minus 1, that is the upper boundary I have, 0x 100f. Okay, so here 1010 is the crossing value, so crossing the 100f. Okay, this 100f is crossing 1010. Then so it is moving to next address, then it is moving to again start address. What is the start address here? This is the aligned address 100. So based on that the aligned address, it is wrapping around to 1000. Okay, so the next address is again 1000. After that next address, how we can assign? 1004, again 1008. Okay, again 100c. Again if we are transferring the next bit, again it is going to 1000. So 1000 it will go that. Okay, in this way we will calculate it. So this is the quick reference, wrapping region, ax length plus number of bytes. So based on that ax length, that means beats, actual beats, and then data bytes. In that way we will calculate the total regions, how many regions we are calculating. So that is the wrapping region we will calculate here. After that ax length, so this is the ax length and then data bytes. Based on that region we have calculated, then aligned address. So up to this 1004 aligned address is 1000, and then 1ff8 is the aligned address, that is the aligned data only, so it is divisible by 4. Then 1 double f8 is the aligned start, then upper boundary. So this address whatever the 1000 is there, so that 1000, and then wrapping boundary, so minus 1 we will get the upper boundary value. And then here also 1 double f8, and then the wrapping region is 8, so 1 double f minus plus 8 minus 1. Okay, plus 8 means 16, 16 means 16 minus 1 means 15, then 1 triple f. So in that way upper boundary we will calculate it. So based on that upper boundary and lower boundary, if it is reaching, then we will calculate the next beats addresses. If it is crossing that next beat addresses, means it is again wrapping around to start address. Clear? So these are the burst types. So reserved we are not calculating here. So this is the quick reference for aligned, unaligned, and then transfers, and then burst based transactions, increment burst, fixed burst, and then wrapping burst. Okay, these are the protocol violations. What are the protocol violations? Handshake violations is there. Okay, how we are designing the handshake, how we are saying that handshaking violation means, so valid should be 1. Whenever that valid should be 1, ready should be 1. If it is valid is ready, valid is high but no ready means, then transfer is not occurs. That is the without valid, without ready condition. That is the error we are getting. And again, AW ready without valid. If you are, the slave is ready but valid data is not there, that is also violation. And then AW is there, but this is the suspicious handshake, because slave is ready but master is not giving the valid data. Okay, so that is the suspicious data behavior. And then here valid is there but ready is there, not there, then we lost the data. Okay, so because that master is hanging on that, so hanging on that, or it is in deadlock condition only, because we, the slave is not responding anywhere. And then again, AW address, what is the AW address we are having? AW address, after that W. First we need to place that AW address, after that only W at W we need to place that, where we need to place the data, that we need to place. So after we are keeping the address, after that we are giving the address means that is invalid. Okay, that slave cannot respond, some decode error will getting. And then W last signal we are not keeping that. That means we are placing that number of datas, but last signal we are not mentioning. That means slave waits for that. So our slave is hanging on that, because we are not putting the last address from the writing side. Master is not keeping the last address signal. W last will be keeping by the master. And again, same IDs are there in your AXI3, but AXI4 is not allowed that. So if it is, if you are using that same IDs for writing, so it is not allowed. Okay, invalid condition. That means ID collisions may occur. Okay, and then response signals. We will get the response from the slave, but this response signal is missing. That means your master is still waiting for the response only, so then it is still in deadlock condition. And then invalid B response. B response means your slave is not respond, your slave is responding, but incorrect data, for that incorrect data you are responding. That means slave error we are getting that. So slave is responding but giving the okay response, but it is not getting the actual data, actual address, then slave error will getting that. And then unaligned accesses, that means it is not giving not multiples of 4. Okay, so that means your maybe some unexpected data we will get, because slave is not having that data, because illegal access we are getting that. And then illegal burst calculation, that means unsupported bursts, AX length and AX size is the combinations. In that some unsupported size you are giving means you may get slave error or unexpected behavior from your slave slide. Okay, so these are the violations. And then timing violations, where we are getting the timing violation, we are maintaining the clock signal is high, so every rising edge of the clock only we are transferring the data, but valid is there in lower clock edge, so this should be the timing violation. So rising edge of the clock only we need to consider that. And then ready signal should be glitch we are getting, so that means this is also rising edge, we need to get the data. But here some high impedance state is there, so valid and ready is there, but we need to maintain the data stable, but high impedance value we are getting that high impedance gives that handshaking mismatch. That means data must be stable during that handshaking signal. Okay, so these are the response codes: okay response, exclusive okay response, slave error, and decode error. If you are getting the decode error means address is failing, and then slave error means your slave is not responding that, so invalid access you are doing that. And then exclusive locked access, exclusive access means you are getting locked or exclusive write access. Normal access means you are getting the response, normal response. So how we are avoiding that? So impact of violations. What is the violations we are? What is the impact while violating the protocol? Your data may be lost, or system may be in hang or deadlock condition, or you are getting the illegal memory access, and then performance degradation. Complexity will be decreases. So this all is impacting. So that may be avoided by using maintain better handshaking mechanism, and AW should be maintained first. After that, that means address phase is followed by the data phase, and then ensure that your data may be completed, means you need to keep the W last signal should be high, and every time you need to maintain unique IDs, because interleaving allowed here AXI3, so AXI4 is not allowed in that. Okay, so then responses may come in any order. So if you don't want that in order only, you need to get that, you need to maintain same ID. Okay, these are the conditions you need to consider while avoiding these protocol violations. These are the practical consideration. Clock and reset signals we need to maintain. So each and every cycle we need to reset that. Okay, reset is asserted and then reset is deasserted, because it is a low state. When you are resetting, all the signals should be maintained 0, and when we are setting the reset, so all the signals should be so desetting the reset, manually we are giving the signals. So during this condition, we are getting the, see, this is the reset condition, setting the reset condition. During the reset condition, all the signals should be maintained 0. And clock domain crossing, so from master to slave we need to maintain proper clock, because in AXI we are having multiple clocks we are using. So because we are having AXI clock and system clock, so these clocks should be avoiding. So clock domain crossing problem should be avoided here. These are the practical considerations we are when you are considering the AXA protocol. And do not cross the 4 KB boundary rule. So we need to maintain the 4 KB boundary. So that means 10x1000 address we need to maintain. If it is crossing, means it is not supporting, invalid addresses we are getting. Okay, so that means your start address may not be start from 0 FFC or FFD. So in that addresses do not cross that. Okay, do not start with these addresses. Then it will definitely cross your boundary. 100 is crossing definitely, because if you add +4 to D, means D is 13. So 13 plus 4 means 17 you are getting. 17 is nothing but what is the value? 1 3 you are getting. So sorry, 16, right? 1 1 you are getting. So that means 1011. 1011 means that is crossing your boundary. Okay, so we need to create maintain that boundary condition, and then unaligned transfers are also supporting. That means we need to maintain the first address should be unaligned and remaining should be aligned. Okay, so at that time we are not giving the valid data, and right strobe signal should be maintained, but that how many data bytes you are transferring, all the byte lane should be maintained valid data. So then only right strobe signal should be used properly. And then outstanding transactions, because while going for multiple transactions, so we need to give the we need to wait for the response. So you are sending the different IDs, the response may come in any order, and if you are sending same ID, so the response come in same order. So out of order you are expecting, so the ID should be maintained different. If you don't want to get outstanding out of order transaction, you need to maintain the same ID. And error handling, okay response, exclusive okay response, all these things. So while maintaining that proper addresses and illegal addresses should be avoided, means so this slave error and decode error should be avoided. Okay, verification considerations, 4 KB boundary, incorrect right strobe signal, in ordering violations. Okay, so protocol violations, all these things we need to consider. Okay, so these are the interfaces. where we are using the AXI interface. For single master and single slave, we are using the AXI interface. Okay, it is allowing that single master and single slave, and also multiple masters and single slave also it is considered, and also multiple single master and multiple slaves are also supporting here, and crossbar connection, that means multiple masters and multiple slaves are also supporting here. Okay, so AXI sometimes we will use it as a bridge type, that means memory to master is sending the data, so that means memory to peripherals, or DMA to peripherals, or CPU to memory. Okay, these type of interfaces we need some bridges, and protocol converters like low speed peripherals to high speed peripherals we want to connect from AXI to APP which we are using, and then clock converters, so one clock is crossing with another clock, so that AXI clock connector is there. Complex interfaces also supporting. So this is the protocol verification, how we are verifying that. So verification objective means ensure your protocol should be maintained proper, so without violating we are maintaining that protocol. And then AXI interface approach, we need to go for different VIPs. Okay, AXA master VIPs and then slave VIP. After that, some functional coverage, port coverage, assertions, checkers, all these things we are using the verification approach. These are the tools we are using: Synopsys, VSys tool, Cadence, Siemens, Aldac, Aldac Reveria, and then open sources we are using. Clear? So coverage models we are considering that in coverage channels, all the channels we are considering. Okay, so all the signals we need to store in the data, and burst types we are considering. We are checking that transactions read and write, and single transaction or multiple transactions, out of order transactions. We are checking all these things. Clear? So and then protocol real life times where we are using the protocol. See, CPU to DMA we are using that. So and then DDR memories and DMA to peripherals, and CPU to or NPU to DDR memory. So display to AXI, display to display panels, all the audio systems, peripheral registers, and we are using anywhere automotive applications. Okay, AXI is the backbone of any protocol, right? So that's why AXI is utilized in everywhere, smartphones and then mobile phones, application processor like CPU and DDR. We are using interconnect, AXI interconnect, and then audio signals, and then DMA to some peripheral devices. We are using AXI protocol. Okay, so this is complete overview we have discussed up to now. What is AXI and architecture of AXI, 5 channels, valid and ready handshaking, transactions, out of order, outstanding, unaligned and aligned transactions, and burst calculation. These are the signals, and then fixed burst, increment burst, wrapping burst, write transaction rules, read transaction rules, write transactions, write strobe signals, and write read response signals, and address alignments, outstanding or ordering rules, atomic accesses, locked access, and exclusive locked access, and 4 KB boundary rules, and common mistakes we are doing in AXA protocol, all these things.